Alright folks, welcome back to the 344 video lectures. These next two lectures are concerned with the broad area of organometallic chemistry. This is an area that you've been exposed to some degree in Chem 343 and Chem 345. Most recently this week we just did the Grignard reaction in Chem 344 lab, and the Grignard reaction it was invented by this dude here, Victor Grignard, French chemist. Very famous, won the Nobel Prize in, I think, 1912. And these Grignard reagents we're going to use as kind of examples of common and useful organometallic stoichiometric reagents. Before we move on, I think it's worth talking about and defining what is organometallic chemistry. So we've got an empty Venn diagram right here, and on one side we can put organic chemistry. As you're all familiar with it, it's the chemistry of carbon. It's a very broad definition, but I think it's pretty applicable. We're interested in structure and bonding and reactivity of carbon-containing compounds. Then on the right-hand side, we can go with inorganic chemistry, which you could say is the chemistry of everything else, the chemistry of everything that doesn't fall under organic chemistry. For our purposes, I'm saying it's the chemistry of metals. Okay, so we've got two kind of spheres of chemistry here, and in the middle is where all the action takes place in Venn diagrams. And in the middle of this Venn diagram, we have the area of organometallic chemistry, which is this really awesome and comparatively recent area of synthetic chemistry that's really come to light. And broadly defined, it's the chemistry of compounds containing direct carbon metal bonds, which might sound a little weird, but if you think about it, you've already seen a few examples of this: Grignard reagents, organolithium reagents, that kind of thing. And organometallic chemistry itself is fundamentally a very interesting area. You get some weird and kind of cool reactivity profiles. You get very different chemistry than you do in organic chemistry and inorganic chemistry distinctly. What we're going to focus on is the ability to use organometallic compounds to do organic chemistry, organic synthesis, that we couldn't do if we didn't use metals. So organometallic chemistry opens up lots of different reactivity to do organic chemistry with. So let's just do a quick review here of the periodic table and how we can define what's organic and what's inorganic and what's organometallic. So on the left-hand side here we have the alkali metals. We should be familiar with these. Primarily lithium, magnesium are the most interesting to us as synthetic chemists. On the right hand side we have the main group, where the p orbitals become filled, and a lot of familiar elements over here. And then in the middle we're going to ignore the lanthanides and the actinides. We have the transition metals. This is where the d orbitals become filled, and okay, fair enough. Next to each of these elements, like here, for instance, germanium has 2.01, nickel 1.91, nitrogen 3.04. That number refers to the electronegativity, or more accurately, the Pauling electronegativity of each element. And we can see that, again, this should be reviewed, that fluorine is the most electronegative element. That's at the top right of the periodic table. And the alkali metals are very non-electronegative, or electropositive, if you wish to call them that. So that's going to be interesting and very useful to us as we move throughout this lecture. And really, we can define a limited number of elements as being, let's call them the regular organic elements. These are the elements that typically appear in organic chemistry, of the halogens, oxygen, nitrogen, carbon. Less so at the 344 level, but certainly we see silicon, phosphorus, and sulfur taking a big role in organic chemistry. If we were being generous, we might extend it to selenium. And a lot of good chemistry is done just in this area of the periodic table. You could argue that the chemistry of life takes place in this area of the periodic table. But if we expand our horizons to include metals, then, as I said earlier, we can consider lithium and magnesium, and to a lesser extent, sodium and potassium. Certainly lithium and magnesium are very synthetically useful when they're in an organometallic compound. And then in the transition metals, this is when the utility really takes off. And I've highlighted just certain metals. That doesn't mean that those that aren't highlighted are not useful. It's just things like nickel, palladium, zinc, ruthenium, titanium have found broad and very useful application in not only organometallic chemistry for the sake of it, but for industrial chemistry, pharmaceutical chemistry, that kind of thing. So really, if we open our horizons to using metals in organic chemistry, we have much more to play with, and that expands our ability to do synthetic chemistry. So let's talk about how we would make some S-block organometallic compounds. You're probably familiar with the idea of organolithium reagents, where we would take some kind of alkyl halide, X is just a halide here, react it with elemental lithium, and we generate, in this case, tert-butyl lithium, where we have a direct bond between a carbon atom and lithium. The Grignard reagents, the organomagnesium halides, they don't have to be just aryl. We can have alkyl Grignard reagents. I've chosen aryl because that's what you're going to be more familiar with in the course. But again, we're taking a carbon, reacting it with an elemental metal, magnesium in this case, and generating a compound, in this case phenylmagnesium halide, that features a direct carbon, in this case magnesium bond. Now, as an aside, you've probably heard of Gilman reagents, these lithium diorganocuprates. We're not really going to talk about those in depth at all, except to highlight that they are actually made from organolithium reagents. This is a typical equation here to make lithium diethyl cuprate, and a Gilman reagent is essentially a alkyl group transfer reagent. That's a very simplistic way of looking at it, but that's essentially what it does. In the second part of this lecture, we're going to come back and highlight Gilman reagents again for a specific purpose, but we're not going to be talking about them in any depth. So what's the reactivity of, let's say, a Grignard reagent? Well, hopefully this is review from 343 and 345, but when we take this Grignard reagent, this phenylmagnesium halide, and react it with, typically we're going to react it with a carbonyl containing group, and when I haven't shown the workup conditions here, but when we acidify the mixture at the end of the reaction, we end up generating two things. First and foremost, probably, a new carbon-carbon bond. We've generated a carbon-carbon bond between this carbon atom and this carbon atom. Whenever we can generate a carbon-carbon bond, that's a good thing. That's a powerful reaction. But what this particular reaction also generated was an alcohol. It converted the carbonyl group of this ketone into an alcohol, and that's got very high utility as well. And similar reactivity happens with an organolithium reagent. Again, we've created a new carbon-carbon bond, and in turn we formed an alcohol. Now, we're used to thinking in terms of typical organic compounds, as the carbon acting as an electrophile. For instance, in this ketone, these two ketones here, we could draw, let's focus on this one, we could draw a delta positive charge on this carbon atom and a delta negative charge on this oxygen atom. So this carbon has a certain degree of positive charge associated with it. But the carbon atom in an organometallic compound, such as an alkyl lithium or a Grignard reagent, has significant carbanionic character. That means it reacts as a nucleophile. They also react as bases, but we're going to focus for now on the reactivity of this carbon atom and this carbon atom as a nucleophile, not an electrophile. And as we can see from the reaction product up here, we've got our carbon electrophile. Our carbon nucleophile must be our organometallic reagent, and the combination of these has formed the new carbon-carbon bond. So one question we should really have is, why do Grignards and organolithium reagents, or rather the carbon atom in a Grignard and an organolithium reagent, why does that carbon atom react as a nucleophile? Well, let's think about the charge distribution in a typical organic compound, and then go ahead and compare that to the similar charge distribution in an organometallic compound. So I've chosen chlorobenzene as an example of a kind of typical organic compound here. And if you could do this yourself, if we compute the NPA charges using WebMO for chlorobenzene, we can see that this is probably what we would expect to see. The blue atoms are those that are positively charged, the red atoms are negatively charged, and we've got our benzene ring here, a carbon atom and a chlorine atom. So let's just kind of show the values here. In the benzene ring, it's no real surprise, we would expect these carbon atoms to be negatively charged. Excuse me. And then when we look at the carbon heteroatom bond, when we take into account the relative electronegativity of carbon and chlorine, we find that chlorine is much more electronegative than carbon, so we would expect this bond to be polarized in the negative sense towards chlorine, and that's indeed what we see. This carbon atom is reasonably positively charged, this chlorine atom bears negative charge. So we could, if we were going delta positive, delta negative, we would write a delta positive on this carbon atom, delta negative on this chlorine, and we would agree that the carbon atom in chlorobenzene is indeed positively charged. Let's take a look at phenyl lithium. I've chosen this as an example of a typical organometallic compound just for comparison with chlorobenzene. All we've done is change the carbon-chlorine bond to a carbon-lithium bond. And on the face of it, there's one big change. Nothing has really changed in the benzene ring, and we might not expect it to. But what has changed is that this carbon atom, which in chlorobenzene was positively charged, is now very strongly negatively charged. And in contrast to the chlorine, the lithium is now strongly positively charged. Let's take a look at the electronegativity values. Well, the electronegativities of hydrogen and carbon certainly haven't changed, but lithium is now much less electronegative than carbon. So the polarization of this carbon-lithium bond is polarized strongly towards carbon in the negative sense, and we could agree that the carbon atom in the carbon-lithium bond is highly negatively charged, and we can now draw a delta negative on this carbon, which implies that it has nucleophilic character. It's going to seek an area of low electron density when it reacts. And if you have time and interest, I would encourage you to just maybe compute some different types of organic molecule and compare them to organolithium or organomagnesium compounds, just really to build up a library of understanding. It's not necessary that you do that, but it would be, I think, a good exercise for you to do. So this idea of carbon-metal bond polarity really can drive the reactivity of organometallic compounds. What we see here is a table displaying various carbon-metal bonds up to this dotted line. The difference in electronegativity, which is taken just by subtracting the electronegativity of the heteroatom, in this case it's potassium down to copper, from the electronegativity of carbon. And we get this difference in electronegativity. And what we can do then is use this simple equation here to get a very rough estimate of the percent ionic character of each of these bonds. And we can see that, we can assume that the percent ionic character is a reference for how reactive this carbon-metal bond will be. So for instance, at the top here, we can see that potassium-carbon and sodium-carbon bonds are very strongly ionic, almost entirely ionic. And that means they're very highly reactive, and that means that they don't really have broad application or really any application in organic chemistry. They're very reactive, very difficult to handle, because the main reason being the bond is so reactive. So we can call those primarily ionic compounds. When we're now talking about carbon lithium and carbon magnesium, Grignard reagents right here, and you see that this is a very kind of broad area here. I don't mean to say that there's a hard cutoff between polar covalent and covalent here. There's definitely some wiggle room. But carbon-lithium bonds represent kind of the first point at which S-block organometallic compounds become controllable. And even then, not every carbon-lithium compound reacts the way we want it to. But we can see that as we drop down in percent ionic character of the bond, we get milder reactivity. And this is really where Grignard reagents start coming in. They're milder reagents. They're not quite as reactive as organolithium reagents. The bond is a slightly less reactive. It's slightly less polar. And as we drop down, we'll see that the bond between carbon titanium, carbon aluminum, and when we get down to carbon copper, granted this isn't this is now a transition metal, the percent ionic character of those bonds drops dramatically. And for comparison, I've just thrown in down the bottom here under the dotted line some common kind of organic type bonds between carbon oxygen, carbon chlorine, carbon bromine, and kind of the classic organic bond between carbon hydrogen. Just as really as a reference point to show you how ionic and how reactive these bonds are at the top end of this table. For instance, if we take the carbon-chlorine bond, we know that chlorine, as we saw in a few slides ago, is more electronegative than carbon. That doesn't really matter when we're talking about the ionic character. That's about 25% ionic character. Carbon-bromine, because bromine is closer in electronegativity to carbon than chlorine is, has much less ionic character. So we generally think of these types of bonds starting probably between carbon titanium and carbon aluminum as being more or less fully covalent. And certainly the carbon hydrogen bond is fully covalent. So I don't want to really talk any more about this. I probably talked too much about this slide already, but just to get the feeling for the percent ionic character of a bond being a surrogate for how reactive that bond is, and that means typically how useful it's going to be in organic chemistry. Highly reactive bonds tend to react indiscriminately, so they're not quite as useful as bonds that are reactive but controllably reactive, let's say. Let's talk about the reactivity of a Grignard reagent here. The reaction that you did in 344 lab on Wednesday and Thursday was the conversion of a Grignard reagent via its reaction with carbon dioxide into the corresponding benzoic acid. And the typical reactivity of Grignard reagents is with carbonyl compounds. That's what we see in sophomore level textbooks, and that's typically where it's exploited, at least classically in organic chemistry. And if you think about it, carbon dioxide is the prototypical carbonyl compound. So we're just going to use this slide too, and the next one to just illustrate why the carbon atom of the Grignard reagent reacts the way it does, why it forms a carbon-carbon bond between this carbon atom and this carbon atom of CO2. So again, using WebMO at a relatively low level, I wouldn't put a whole lot of stock in these numbers, but the relative signs of the charge are certainly correct. In this Grignard reagent, it's phenyl magnesium halide. Let's say this is chlorine for the sake of argument. We can again see that the carbon atom is negatively charged. It's less negatively charged than we saw in phenyl lithium by about either 0.1 or 0.2 of a charge unit. I don't recall, but it's certainly lower. And we got to recall that the carbon atom of bonded to the magnesium atom in phenyl magnesium, turns out it's a bromine, not a chlorine, so this is phenyl magnesium bromine, is nucleophilic. And that's in stark contrast to typical reactivity of classic organic reagents. Just for reference, the percent ionic character of the carbon and magnesium bond is about 50%. We just got that down here. And if we do the same NPA charge calculation on carbon dioxide, we see that the carbon atom of carbon dioxide is highly positively charged. This oxygen has about half a unit of negative charge, and so does this one. I haven't displayed it, but it certainly has equivalent charge to this oxygen. So from a whether it's an electrophile or a nucleophile, this carbon is clearly an electrophile because it bears almost a full positive charge. Again, I wouldn't put a whole lot of stock in the actual magnitude of this, but the sign is certainly correct. So in terms of identifying our nucleophile and our carbon nucleophile and our carbon electrophile, our charges take care of that. We can see how the bond is formed from the nucleophile to the electrophile just by looking at the charged the charges of each of the atoms that are taking place in this reaction. Well, if we can go a little deeper and think about the molecular orbital picture of this reaction as well, because we know that a nucleophile brings a HOMO to the reaction. That brings an occupied, that supplies the electrons essentially, and the electrophile brings the LUMO, the unoccupied molecular orbital. And if we take a look at the LUMO of carbon dioxide, this is the acceptor orbital. Again, these are the charges on the oxygen and the carbon atom, just transferred from the previous slide. And we'll see that I haven't shown the highest occupied molecular orbital of this Grignard reagent because it was actually a little difficult to visualize. But we can assume that the HOMO has significant buildup of electron density in this area. And of course, an interaction between a HOMO and a LUMO is what drives bond formation. And we can see that for carbon dioxide, the largest lobe of the LUMO is placed on carbon. So everything is consistent here. Our nucleophile brings its highest occupied molecular orbital and transfers electron density into the lowest unoccupied molecular orbital of the electrophile. So everything is consistent here. And then upon acidic workup, we, as we see here with HCl, and as you did in the lab, we generate the corresponding carboxylic acid. So this is the first step of the reaction, transfer of electron density from the carbon-magnesium bond into the acceptor orbital, into the LUMO of CO2, the largest lobe of which is present on the central carbon atom. So that's a very quick overview of S-block organometallic chemistry and why a Grignard reagent reacts the way it does. It's because of that kind of polarized bond, which is polarized in the negative sense towards the carbon atom, which is different to classical organometallic chemistry. What I want to do now is just review some questions you may have had either going into or coming out of the lab that you did on Wednesday or Thursday in Chem 344. And the first one, the common question is, why did we need to use an anhydrous solvent and a drying column when we perform this reaction? Why did we need to pay attention to the reaction conditions? Remember, an anhydrous solvent means that there's no water in there. It's been dried, free of water. Well, let's think about the reactivity of a Grignard reagent towards water. I've already said that the Grignard reagent, this carbon atom, is highly nucleophilic, but it's also a very strong base as well. This is the conjugate base of benzene, and we know that benzene has a pKa of about, I think it's in the low 40s, let's say it's 43, 43.5, something like that. So this is a strongly basic carbon atom. And if we have a source of relatively acidic proton, what's simply going to happen is, instead of getting any kind of useful reactivity, we're going to just perform an acid-base reaction, in this case between this carbanion type carbon here and one of the protons of water. So the base abstracts the proton from water, and we essentially form benzene, which is not really what you want to do in a Grignard reaction, and this magnesium salt byproduct. We have so the pKa of benzene, of which this is the conjugate base, is about 43. pKa of water is about 16. Essentially, water quenches the Grignard reagent as it forms. So as soon as that Grignard reagent forms, if there's water present in the reaction flask or in the solvent, then it just quenches the Grignard reagent. It stops it reacting the way we want it to react. So this is not really very useful at all. Another question that students come out with is, okay, I get the need for an anhydrous solvent and keep everything dry, but why do we use diethyl ether specifically? Diethyl ether is a little bit hard to handle sometimes because it's quite volatile. It has a boiling point around 35 degrees. So oftentimes that's kind of difficult to handle. It sometimes evaporates before you want it to. Why can we not use dichloromethane or hexane or something similar? Well, we use diethyl ether and ethers in general because of their ability to form weak bonds, kind of sticky bonds to the magnesium atom of the Grignard reagent. These are certainly not classic two-centered two-electron bonds. It's really a transfer of electron density from the one of the lone pairs of the oxygen atom to the magnesium atom. It just kind of calms down the reactivity of the magnesium atom. what I've got here is a representation of phenylmagnesium bromide with two diethyl ether molecules attached directly to the magnesium. This is not a crystal structure, this is just a theoretical picture of it. It's really just to illustrate a point. You'll see that the magnesium atom is bonded to the carbon atom of the benzene ring, which you would expect, and to a bromine atom. It's also bonded to a pair of diethyl ether molecules by the oxygen. And if we were to draw this in kind of chem draw lecture style, we would probably draw these two bonds as arrows rather than as direct oxygen magnesium kind of two-centered two-electron bonds. But suffice to say that when we have a coordinating solvent such as ether or tetrahydrofuran or dioxane, this tends to stabilize the Grignard reagent and makes it more soluble as well. We want these magnesium reagents to be entirely soluble, and we want them to be homogeneous. That's a word we'll define in the next part of the lecture. But we want everything to be in solution as much as possible. We don't want it to be this compound to be stabilized too much. We certainly want it to be reactive, which is why coordinating solvents such as ethers are useful, because they stick, if you like, to the magnesium to just the right degree. And then, once this has been explained, some students have the question, well, is it really accurate to show a Grignard reagent as being, just a phenyl magnesium bromide? Because I've just told you that that's not really the case, because we have kind of shrubbery attached to the magnesium atom. Is this a realistic representation? Well, the answer is no. It absolutely is not a realistic representation across all occurrences. And indeed, there's a thing called the Schlenk equilibrium, which was discovered and studied shortly after the discovery of the Grignard reagent itself, wherein that in solution, these two molecules of any Grignard reagent, R is just an organic group, disproportionate and in fact go through a dynamic equilibrium to produce a molecule of this diorganomagnesium compound and a dihalomagnesium salt. Now, we certainly don't want to get too involved in this. This is a very, very complex area. The position of this equilibrium depends upon the nature of the R group. It depends on the nature of the solvent, the temperature, the concentration, the nature of the halide. Suffice to say that in solution, the behavior of Grignard reagents is very complicated. There are many, many different reactive species, all present simultaneously to some degree in any solution of a Grignard reagent, again, depending on reaction conditions, solvent, temperature. But this formulation, this kind of single molecule RMGX, works perfectly at our level just to explain in a simple way the mechanisms and the reactivity of Grignard reagents. So we should be aware that, like a lot of things in chemistry, if you scratch the surface, you see a lot more detail and there's a lot more complexity. But really, that doesn't take away from the fact that we can explain the reactivity of Grignard reagents just by using this kind of single molecule idea. So let's just summarize real quick here what we've discussed. We've defined organometallic chemistry as the chemistry of a carbon-metal bond, essentially, and it kind of sits at the intersection of inorganic chemistry and organic chemistry, and it has all kinds of uses, from the fundamental and kind of curiosity-driven up to pharmaceutical and industrial synthesis. In essence, it allows us to broaden our horizons for doing organic chemistry. We spoke about organolithium and Grignard reagents, primarily Grignard reagents, and know that those are highly polar bonds where the carbon atom is highly nucleophilic and strongly basic. So that we have to pay careful attention to reaction conditions. We typically use Grignard reagents in reactions with carbonyl groups. And one thing that I didn't really talk about, but I will highlight in the next part, is their use in a stoichiometric amount. That means that whatever carbonyl group or carbonyl containing molecule that we're going to react a Grignard reagent with, we need one equivalent, at least one equivalent of the Grignard reagent to perform that reaction. That can become limiting in some ways for the utility of organometallic chemistry, because, as we've seen, the organolithiums and organogrignards are quite highly reactive. So if you need a lot of that in the flask, there's the potential for side reactions, there's the potential for uncontrollable reactivity. There's the potential for some things that we don't want to happen. And we'll see in the next lecture that we can use different types of metals to perform reactions in a catalytic manner rather than a stoichiometric manner. And then just to kind of summarize what you saw in the Grignard lab, the need for using dry glassware and dry reaction solvent is totally a function of the fact that the Grignard reagent is a strong base. And if we have water in there, then the Grignard reaction will just react to form, the Grignard reagent rather will just react to form benzene. It won't react the way we want it to. And then finally for the lab write-up, this is a new thing we're doing this semester. It's a new Grignard reaction. The best advice I can give you is think back to what you covered in chapter 5 in the WebMO introductory material, and think about the strength of each carbon-halogen bond in the starting material that you used for the Grignard reagent. We have a carbon-fluorine bond and a carbon-bromine bond, and think about which one of those is more reactive towards the insertion of the magnesium atom into that carbon-halogen bond. So that really kind of concludes this part of the introductory organometallic lecture. So feel free to ask Dr. Esselman or myself or even your TA if you have any questions about anything that's gone before. And we'll wrap it up here, and then in the next lecture I'll talk about some transition metal chemistry, and we'll move into talking about catalysis and how we can kind of deconstruct and analyze a catalytic cycle.